Any other answers other than the ones we have? All right, so what we're doing today is we're talking a little bit about how many ways are there to combine a fixed number of certain bricks. All right, so given that everybody got 3 for the 2 by 2, all right, were you surprised that that's easier or harder than the 1 by 3? So a lot of it really matters how the combinations are coming. What about the 2 by 3? Was that significantly harder than the others? What if we had to add a third level? So one of the ideas for tackling these problems is you want to try to break it up into smaller problems and combine things. And so one thing is, maybe if I know how to combine one brick on top of another, I just have to do this one more time. Right? Or maybe if I know how many ways there are to put one brick on top of another, then that's 2. Then I'll look at all the ways I can put that on the base. What's the problem with that approach?
Putting 2 blocks the same level on top of 1.
So one is, do I have the possibility of putting 2 blocks on the same level? So maybe we'll make the problem easier by saying if I have n bricks, I have to have something that's of height n. So I don't have to worry about 2 bricks of the same height. One of the dangers with that is I could have 2 bricks on the same level not connected and then another one above it connecting it, which can make the problem really challenging. So let's assume that you have to be increasing in height. Why might the problem be more complicated than just saying, well, look, I look at all the ways if I have 3 of these bricks now, that I can do 2 of them, and then I put all those on the base. So one of the problems you might have is, depending on how those 2 bricks are already stacked together, you might be able to put them several different ways on the first one and have them equivalent under rotation. But if they're stacked differently, maybe you can't put them down in the same way and have them the same under rotation. So it could get to the point where you have to really split by what are the different shapes, what are the different equivalence classes. And then maybe if you have a subject that doesn't have any rotational symmetries, maybe then you can just see how many squares can I physically put that down. And so you might be able to take a complicated problem and break it up into a lot of smaller, simpler ones. So how many of you have studied recurrence relations? Okay. How many of you have seen the Lego Batman movie? All right. So this will test how well you remember the great lines. And of course, the best line is, of course, why the object that Batman built had only 1 seat. But early in the movie, Batman gives some advice when he's disguised as the mayor to the Joker. He asks him, the Joker, if you like playing games, he asks about a very specific game and suggests a strategy. For real Lego minutia, extra credit. What was the advice Batman gives? And what was the game? All right. Game was Roulette. Anybody know the advice Batman gives in Roulette? Yes?
Don't play, maybe?
Nope.
Negative odds?
Nope. You shouldn't play. That's the correct solution. So the way Roulette works is typically you have 18 reds, 18 black, and 2 green. And typically what you can do is you can say bet on red, bet on black, and if you bet $1 on red and red comes up, you win $1. If you bet on $1 on red and either black or green comes up, you lose. What's your probability of winning if you bet on red?
It's like 49% or something.
Yeah, it's a little bit less than 50%. So the 2 greens really help Vegas. Right? I'm not allowed to do this in the real world, but since this is a math class, let's get rid of the greens. All right? Vegas will not do this. Vegas likes the greens. But let's get rid of the greens. Now what's your chance of winning? 50-50. So the advice Batman gave was always bet on black, which if you think about his preference for building is not unreasonable. So I'm going to show you a strategy called DoublePlusOne. And under some assumptions, this will allow you to go to Vegas and win a fortune. What must be true about those assumptions?
Love large numbers. Do you play a lot?
I'm here teaching you and I'm not in Vegas. What must be true about those assumptions? Yes.
Would you just have to have like an infinite amount of money to like win every time?
So at one of the assumptions we need is I call the eccentric rich uncle aunt hypothesis. I hypothesize I have an eccentric family member who, whenever I need money, will provide money to me to make a bet. If I need $1 billion, they will give me the money for the bet. They won't actually give me any money to keep, but they will bankroll me. Economists love assumptions like this. However, given the fact that I'm here lecturing you and not in Vegas, what else can you say about the assumptions or my love of teaching? Yes.
Assumptions are somewhat unreasonable in real life.
More than unreasonable in real life.
They're impossible.
They're impossible. They must fail. So what I want to show you is the idea of setting up a recurrence relation is trying to figure out a future event based on earlier events. You've seen recurrence relations if you've seen the Fibonacci numbers. 1, or maybe 0, 1, 1, 2, 3, 5, 8. So each number is the sum of the previous two. And once I specify the first two numbers, the pattern is fixed. So the n plus first Fibonacci number is the nth plus the n minus first. We would love to do something like this for the Lego problem. We would love to reduce how many structures there are with n bricks to questions involving structures with previous ones. And you can look at some of the math papers where they try to do this. I'm not going to go through all the math. I want to just go through some of it and give you an idea of how you attack a variety of problems. All right? So let's take Batman's strategy of always bet on black. Okay? So here's the DoublePlusOne. Start. You bet $1 on black. There are two possibilities. If it comes up black, what happens? You win, up $1. If black, up $1, else you're down $1. Is the dog coming in or? Okay. I actually had a friend who was walking a dog recently, and I'm wondering if that's one of the dogs I know. So let's imagine it's red, so you're down $1. What should you do?
Keep playing.
How much do you bet now? Not $1, because if you bet $1 and you win, you're just back to being even. How much do you bet? $2. So now bet $2. So if red, bet $2 on black. If it's black, what happens? So if black, up $1, else what? Down $3. How much should we bet on the next round? So if red, bet $4 on black. Eventually, a black will come up. Once the black comes up, how much are you net? $1. Lather, rinse, repeat. The shampoo instructions for life. You will eventually net $1. And then you just keep repeating this until you make as much money as you want. So what's wrong with the strategy? I must really love teaching Williams students.
Yes.
The odds are still less than half.
But I just have to wait long enough. Even if I had the two greens, this analysis would still work. It would no longer be a 50-50 chance. So it might take me longer, but once I get a black. So Vegas has some really good mathematicians and psychologists on staff. What they now do is when you have the roulette wheel spinning, they display the results of the past couple of rolls or spins. And the reason they do this is you can split a lot of morons into two classes. One class of morons is like, oh, black has come up 5 times in a row. Black is on fire. I'm going to bet on black. What's the other type of moron? Red is due. It's been black for 5 spins. It must be red's turn. Vegas doesn't really care which type of moron you are, as long as you're willing to bet money. They just want people betting money. So one problem with this is that it might come to the point where I have to put down $1 billion. Okay? This is where the eccentric rich aunt-uncle hypothesis comes into play. I assume I have a family member who will not give me $1, but if I need to put down $1 billion, they have so much credit at the casino that they will give me the money and the casino will allow me to place the bet. This is not a reasonable assumption in the real world. Most of us do not have a eccentric rich aunt-uncle. If any of you do, please see me after class, preferably with your eccentric rich aunt or uncle. But let's assume that. Let's assume we have no limit to how much money we can bet. There is another problem, and for this problem you need to know a little bit about how roulette is actually played in Vegas. So does anybody know how roulette is actually played in Vegas?
They put the ball into the thing.
So they put the ball in, it spins, and it comes up the numbers. But there's something about the betting that I have not described.
Is there like a minimum bet you have to make?
There's a minimum bet. And what else do you think there must be if there's a minimum bet? A maximum bet. And they have a minimum and a maximum, and they choose these numbers very carefully. Vegas has the right to refuse to serve you. If you're playing blackjack and they think you're counting cards, they have a really nice room to have a conversation with you. And it's really nice because you don't have to worry about any distractions in that room. They can have a really nice private conversation with you if they think you're counting cards. They don't have to take bets. They typically set up the bets that they think will help them. Ideally, what they want is they want half the people putting money on one side and half the money going on the other side, because they get a cut of the winnings. They get a cut of the bets that are placed. And so they want to equalize so that they are minimizing their exposure. Imagine there's a maximum limit. Maybe the minimum bet at our table is $1, and maybe the maximum is $30. Well, let's say $40. Let's make it even higher. Let's make it $50. So let's see what would happen. So imagine we bet $1 and we lose. And then we bet $2 and we lose. Then we bet $4 and we lose. Then we bet $8 and we lose. Then we bet $16 and we lose. Then we bet $32 and we lose. Now what happens? Yes?
Could you bet on black twice with 50 and 14?
They would not let you do that. Now what you could try to do is you could try to have a compatriot at the table. And you could do this for a little bit of time. But eventually the number would get so large that you would not be able to have enough people at the table to make the bet. So you need to bet $64. The maximum you can bet is 50. So what happens is when you lose big. And when you win small. Vegas loves it when people think of stuff like this. They don't mind if 90% of people leave Vegas going, I beat Vegas, I left with money. It's great for them because then people will go and tell their friends. All they need is a small number of people to lose big. And when you do this system, you lose big. So the question is, how would you calculate the probability of busting? So we can do the problem many different ways. I'm going to do an easier problem than this. Let's just say you bust if 3 consecutive reds. In Vegas, it's going to be more than that. But I want to do a smaller number so that we can just analyze this in a reasonable amount of time on the blackboard. And I want to give you a sense of how you can use math to attack problems. And again, one of the goals could be to try to attack this brick counting problem. All right? So let's let AN be the probability we get 3 consecutive reds in n spins. Okay? One of the interesting things in mathematics is sometimes it's easy to calculate the probability something doesn't happen. So like if you're a Patriots fan, it's easy to calculate what's the probability you don't make the conference championship. So let's let Bn be the probability do not get 3 consecutive reds in n spins. What's the relationship between An and Bn? They sum to 1. So an equals 1 minus bn. If I can calculate bn, I can calculate an very, very easily. Okay? So let's see. I'll come over here to try to keep them on the main part. All right. So let's try to calculate the probability we do not get 3 consecutive blacks in n spins. So here's our start. We bet $1. Half the time we get a red, half the time we get a black. What is the probability we do not have 3 consecutive reds in n spins, given that the first spin is black? So this is the hardest part of the analysis. If we get this right, the rest is downhill. How can I write down the probability of not having 3 consecutive reds in n spins if the first spin is black? It's a sub n minus 1. Because the first spin was black, I can ignore it now. And now from this point onward, it's just going to be, I now have n minus 1 spins to do. This one started off with a red. Could this start off 3 consecutive reds? Hell yes. All right, so, I'm sorry, yes. So we'll split it up into red, black. Each of these happens with probability 1/2. I could keep track of how much I'm betting, but right now I'm just trying to calculate the probability, so I don't really care about the wagers. But the wager would be $2 in this case. What's the probability I don't have 5 consecutive reds, given that my first 2 spins were red followed by black? A sub n minus 2. Now I split this one, and I am running out of blackboard space, which is not great. Each happens with probability 1/2. What's the probability I don't have 3 consecutive reds, given that I start off red, red, black? So that would just be an minus 3. All right, do I have to split this one? What's the probability I don't have 3 consecutive reds, given that I start with 3 consecutive reds? 0. Now you can see why it's much easier to calculate. Oh wait, these are BNs, not ANs, right? BN is the probability you don't have consecutive, sorry. So these should be BNs. Now you can see why we want to calculate the Bs rather than the As. Because this tree just dies here. So my initial quest is to calculate Bn. Bn is going to be 1/2 Bn minus 1. That's the probability I end up here. Plus 1/4 Bn minus 2, plus 1/8 Bn minus 3. So I get Bn is 1/2 Bn minus 1, plus 1/4 Bn minus 2, plus 1/8 Bn minus 3. It turns out that there's a way to solve this and write down a closed form expression that will give you the value of this for any n. Let's try to calculate some values of b by brute force. What do you think the easiest value of n would be to compute? B0. What's the probability we do not have 3 consecutive reds, given that we spin 0 times? 100%. All right, what else is pretty easy to calculate? Yep, B0 equals B1 equals B2 equals 1. Now that we have these, we can calculate B3. So B3 would just be 1/2 of 1 plus 1/4 of 1 plus 1/8 of 1, which is 7/8. And if you think about that, 7/8 is a very reasonable answer. We can then calculate B4, B5, B6. You can write an Excel program and just march down the columns. So for those of you who are not here today, you will write the Excel program and calculate what is B100. Okay? If you try to do instead 3 consecutive reds, if you do 5 consecutive reds, the probability is, I think, around 81% that you will have 5 consecutive reds in the first 100 spins. The probability is extremely high. And that's why Vegas loves it when people think about something like this. But this is if you've seen differential equations, this is a difference equation It's a discrete version of a differential equation. There are an enormous number of things that can be modeled by this, and there's a lot of great mathematics in terms of how you would solve this. There's actually an explicit formula to jump to the 100th term. So you don't actually have to go through all this. So this was a real math class as opposed to like a half math class. We'd actually derive the explicit formula. If anybody's interested, send me an email and I'll give you some stuff to read on things like this. So the question is, can you apply stuff like this to the Lego problems? What are the issues you have in trying to reduce to something earlier? Right? I want to end today with just one more just general fun math fact about how to look at problems in a different light. Okay? So, how many minutes are there in an hour? How many seconds in a minute? How many of you know the metric system? Do you like the fact that we have 60? What's so great about the metric system? Base 10. Is base 10 a really good base? Who is it a good base for? Us, right? For those of us who are doing science in the real world, 10 is good. We have 10 fingers. We have 10 toes. Okay? What base do computers like? 2, sometimes 8, sometimes 16. Computers love powers of 2. How many megabytes are in a gigabyte? 1,024. Even though if you look at mega and giga, I'm sorry?
Didn't they change it so it's exactly 1,000 then?
Somebody please look that up right now, because I will go ballistic if they've changed that. I mean, it was bad enough when they made Pluto a dwarf planet and downgraded it. I'm sorry?
It says 1,000.
They've changed what? Real? No. No, they haven't done this.
I'm backing her up.
Just to warn you, if this is not true, if I search right now, anybody who says that this is true, if I search right now, you will flunk this class. Do you want me to search right now? I'm typing it in. Do you want me to search? Yes or no? Oh my God. Wow. Oh, this is terrible. Wow. Because there are the emails that go around that Oscar the Grouch no longer lives in a trash can, he now lives in a recycling bin these are all fake emails and whatnot. Or the reason it's called KFC and not Kentucky Fried Chicken is they don't serve real chicken, so they can't have that as part of their, I just wanted to make sure this was not one of those joke emails. Wow. All right, in the old days, there used to be 1,024 megabytes in a gigabyte because computers worked base 2, and 2 to the 10, it was just very convenient to work that way. Why do you think we use base 60? I mean, we have 60 seconds, 60 minutes, yes, 360 degrees. So 60 has a lot of factors based on its size. So if we factorize 60, you can do it at 6 times 10. And then 6 is 2 times 3, and 10 is 2 times 5. So if you look at all the numbers that divide 60, you have 1, 2, 3, 4, 5, 6. You don't have 7, you don't have 8, you don't have 9, you have 10, you don't have 11, you have 12. You have a lot of factors. You have a lot of ways of dividing up 60. If you go back to ancient civilizations, it's really good to have lots of ways of dividing up your number. So in terms of just doing things as fractions, how many 60ths? There's a lot of different ways you can split it. How many of you know your multiplication tables? I see a couple of people shaking their heads. Up to 10. Does everybody here know their multiplication? If I say 8 times 7, people know what 8 times 7 is? Also known as 7 times 8? Yes? Okay. Everybody knows up to the 10s. Do people know up to the 11s tables? Yeah, 11's not too bad. The only one you really have to remember is 11 times 11. What about the 12s table? All right, 13s table. Okay. Why don't we have to really worry about the 13s table? 13's prime. But why don't we have to worry about a 13's table? Why don't we teach our kids the 13 tables or the 14 tables or the 15 tables?
We teach them this?
No, we don't. We don't. Why don't we teach them that?
Because they are divisible by 60.
I'm sorry?
Because 60 is divisible by 13.
Well, I'm saying in modern day America or throughout the world, we don't teach tables like the 13s, the 14s, the 15s. Why do we only teach the 10s table?
It's not worth the effort.
Okay? But why is the 10s table sufficient? Yeah, you could do basically repeated multiplication. If you're multiplying the number by 21, you first multiply things by 1, and then you multiply the other one by 2, and then you just shift things, and then you add. You really only need to learn your tens table because we're working base 10. All right. So if you're using your tens table, how many multiplications do you need to learn? 100. All right. So 10 table is 100 facts. All right. That's a lot of facts. Can you make it a little bit better than having to learn 100 things? 50. Why 50? Because things repeat. So you might correct this down to 50, but then you realize that's not quite the right correction. It's going to be higher because what you've done is you've double counted 1 times 1, 2 times 2, 3 times 3, 4 times 4. So you have to actually correct that and move it back up to 55. Another way of looking at it is I can look at 100 and throw away the 10 numbers that are just squares. Divide that by 2 because 3 times 4 is the same as 4 times 3, and then add back the 10 squares. And that's how many numbers I need to learn. So this would be 45 plus 10 is 55. Right? Is it unreasonable to expect you to learn 55 facts? No, and some of them are pretty easy. The zeros table, the zeros and the ones don't really cause that much trouble. Right? Imagine you're an ancient Babylonian. Right? You have your 60s table. So naively, you might think 3,600 facts. Yes. This is before that, actually. So how many facts would you have to memorize? So 3,600 minus 60 over 2 plus 60. At this point, the minus 60 plus is not really making too much of a difference. So if I forget about this over here, that'd be 1,800 and then plus 30. So I think this is 1,830. That is a lot of facts to remember. Right? How would you remember all those facts? Yeah. Yes?
I mean, as a hunch, some of them should be pretty easy.
Some of them should be pretty easy, but a lot of them are going to be painful. Do you want to remember this many facts? No, what would you have instead? Before Jesus, before Google.
Abacus.
I'm sorry?
Abacus.
So an abacus would allow you to be doing calculations. Big tables. Tables of facts. And so I actually brought in today, it should be here. I'm sorry? No, I did not bring a table. I brought in 2 different types of slide rules, I believe. I'll just take out a standard one. So for a long period of time, slide rules were terrific ways for people to do calculations. Now this is actually not as good of a one as the other ones I have at home, but this should come out. Yeah, it's not. Yeah. No. I got this from family members. It's been a long time since it's been used, and it's a little hard to move things out. But you can begin to see you can slide one of the things down, and you start to use it to align things to do calculations. So there are ways to do calculations quickly by using previously stored facts. And the slide rule is actually a really good way of recording a bunch of facts and then doing some additional computations. For the Babylonians, you would have to record on the order of 2,000 facts. So what I want to show you is one of my favorite ideas in mathematics. So already this is a phenomenal idea. This is the idea of the lookup table, that you reduce what you need to do to some facts that you store and then you build off of this. The Babylonians had an interesting way of multiplying numbers. So if you want to calculate x times y, this is x plus y squared minus x minus y squared divided by 4. Okay? So rather than multiplying two numbers, I'm going to do two subtractions, an addition, two squares, and a division. Sometimes you take a step backwards, or several, in order to take a step forward. Let's look at the things. Which is easier to do, multiplication of big numbers or addition, subtraction of big numbers? Addition and subtraction, much, much easier. If you have your two 5-digit numbers, you're going to do all the different combinations when you're multiplying. With adding, it's just, boom, much easier. It's on the order of number of digits, not number of digits squared. When you square x plus y squared, you get x squared plus 2xy plus y squared, x squared minus 2xy plus y squared. The x squared, y squareds cancel. You're left with 4xy up top. You divide by 4. Why is this an advantage? Why would you rather do two subtractions than an addition? Yes? Yeah, you only need to know squares. You might have to do 120 because you might have numbers a little bit larger now. But it's a significant savings. Other ways, sometimes people have done it, sometimes it was x plus y squared minus y squared over 2. That's another way of doing it. This is, I think, the most clever way of formulating it. So I wanted to just leave you with this to ponder, that a lot of times when you have a calculation to do, there's a straightforward brute force approach that will work. But if you are willing to take some time and think about it, you can often find a better way of doing it. And it's worth spending that time if you have to do the problem many, many times. If you only have to do the problem once, it's often worthwhile to just do it by brute force. So I will leave as a challenge for the people who aren't here. Those of you can just ponder this if you want. Take the numbers 1 through 9. And I want you to form 3 fractions where you use each number once and only once. So 3 fractions, 1 digit over 2 digit. And I want them to sum to 1. So for instance, maybe it's 3 over 57 plus 9 over 81 plus 4 over, 62. And the answer for this one would be no, that one doesn't work. There's a way to arrange the numbers 1 through 9 so that you can get this to work. I remember I was at a math institute many years ago and somebody posed this problem, and I'm surrounded by some of the top number theorists in the world, and they start proving results about where certain digits must be. I wrote an extremely inefficient Mathematica code to just go through all possibilities. I didn't bother making the code efficient because it would have taken me more time to make the code efficient than to actually just have the inefficient code run once. And so you can think about how efficient you need to do. How many times am I going to have to run this program? I'm sorry? The program. Once. So if I'm only doing something one time, do I have to be that efficient? No. And in fact, if it's going to take me an hour to have a 50% decrease in runtime, is it worth it? Not if the program takes on the order of a few seconds. If the program takes 3 weeks to run, then yes, it's worth spending an hour. But if I only need it once, I don't have to worry about being too efficient. If you have something that's being done many, many times, then any small savings propagates. And so the question is, how would you find a way to put the numbers in here? All right, so this is a good place to start. We'll have one more class on Friday, and then I want to just talk briefly with the Lego idea people.